Actually, I think my talk may be a little bit misplaced because I'm not doing applied machine learning, although I'm going to set the framework so you can apply all kinds of interesting machine learning here. And the context for this talk is trying to explore how you can use computational self-awareness models to help build dynamic systems. In particular, I'll talk about how you can use that for adaptive resource management. And the work's done jointly with a bunch of some of the bright students from my group, including Thiago Muck, who just joined on research in Austin recently. So, the title self-awareness sounds very daunting. And if you think about what it is, it comes from, of course, the history in biology and in living things. And one specific aspect of self-awareness is this idea of having the capacity for introspection, which requires the idea of having a self-model of oneself. So introspection requires you to build a self-model, and you can use that self-model to do interesting things. So I'd like to walk you through some of the ideas in terms of how you can use that metaphor in trying to build more adaptive systems. So computational self-X properties, it's a buzzword today. You can hear, you go to almost any conference, you'll hear about all of these self-X properties, such as self-configuring, self-healing, self-optimizing, self-X. But there are two key aspects that really contribute to building these self-X models. The first is this notion of self-awareness, which is the notion that in any system, you can build a model of your self-states and behaviors over time. And the other is the notion of the context awareness, where that system lives in an environment, and so you have to understand the environment and how it operates in that operational environment. And based on that, there's been a bunch of work in the adaptive systems community that has come up with categorizing what these self-X properties are. And so we'd like to use those kinds of ideas in trying to build these adaptive systems. And so in this talk, what I want to do is, in the short amount of time we have, I'd first like to talk about, so why bother? Why bother with self-aware chips or something that includes self-awareness? Having done that, I want to talk about three specific topics. The first is this notion of cross-layer sensing and actuation. And this really follows a thread that we've heard in this conference, in this meeting, since, with the keynotes and some of the discussions in terms of, if you live in a connected world, if you're looking at IoT and other kinds of devices, you really need to do sensing and ubiquitous sensing across the stack and actuation as well. So we'll look at a metaphor for how you can do that. Having done that, I'll give you a glimpse of how you can build these self-aware chips using a prototype. And then, awareness and self-awareness is good, but if you try and don't contain or constrain these behaviors, you could be in trouble. So I'll also talk about some ideas in terms of how you can control this so you can have some behavior that you'd like in the future, which is using the notions of supervisory control and coordination. So why on-chip self-awareness? I'll sort of walk through this very quickly, but there's sort of three dimensions of variations that today's chips are faced with. The first, of course, is manufacturing variability that we're all very familiar with, right? The second is environmental variability, which is the idea that these chips may be faced with variations in temperature and radiation and things that happen in the environment. And the third dimension for many of these chips is application variability. No matter what kind of system you're looking at, they go through a lot of adaptation in terms of the runtime. So you take a mobile system, for example, that's a perfect example where you might be doing browsing, you may be talking on the phone, you may be watching a video. So the dynamics of the stress that's put on the system is quite variable. And so I posit that it's very important to have some self-aware mechanisms that can deal with these types of variabilities. And the second is something that we heard from the CTO's keynote yesterday, which is that it's not about performance only. It's about trying to deal with multi-dimensional constraints. So how do you deal with performance, power, resilience, security? And these things change over time. So at some instance, some epoch of time, maybe you're really performance-driven. At some other time, maybe you have a thermal design emergency, and you may be worrying about security at other times. So how can you build these systems that can adapt to these different constraints over time? And so that's sort of the idea of being able to dynamically manage multi-dimensional trade-offs across various dimensions and to satisfy different constraints at any time. Now, this is not an easy task. And in fact, if you don't have ways to control it, you might be in trouble. So you must also try to understand how you can provide some level of guarantees so you can actually achieve those over time. Otherwise, you have unbounded behaviors. So I think that there are a lot of lessons to be learned from trying to exploit this notion of computational self-awareness. And I'll try and give you a glimpse of how you could do that through two projects that we've done recently. So to do that, first, I think I want to emphasize something that we all know about, but we haven't been maybe thinking about it that way, which is this notion of cross-layer sensing and actuation. So this cartoon here shows a typical stack of, let's say, a mobile system. So you might look at this mobile system at different levels of abstraction, right? I just picked a few here, like device, hardware, network, operating system, application, but you can take your favorite stack. And what we typically do is we sense information across the stack, different types of information. And that's what you see here on the right-hand side, where you're sensing different kinds of information. And then what you might do is you have some policies that allow you to effect actuations again across the stack. So DVFS is a good example, where you might sense something at the scale of an operating system level, and then you go back and then maybe you're actuating something at the device level where you change the voltage or the frequency. And examples of this abound. And in fact, we're doing this all the time when we have systems that we're trying to control. So to be more specific, this picture, this seemingly complex table really tries to show you these layers that you saw earlier and gives you some examples of the virtual and the physical sensors and actuators. So for example, at the device level, you could have physical circuits that measure circuit delay, aging, leakage, temperature, oxide breakdown, et cetera. And the actuations that you might do are physical things such as DVFS, DFS, adaptive body biasing, et cetera. You might move up the stack and you might go to, let's say, the network or bus level. And here you might have something where you're looking at bandwidth, packet flit status, channel status, congestion, et cetera. And the actuations might be at something like adaptive routing, bandwidth allocation, channel number, et cetera, et cetera. So with this metaphor, what we can do is we can try and reason about how you can get information at different levels and actuate again. So this is a very important abstraction that we should be thinking about. Having done that, let's take a look at what do I mean by self-aware chips. So I'm going to use a lot of cartoons here and metaphors, because I think that's easier to kind of grab in a short amount of time. So the first notion of self-awareness is this notion of self-reflection. And this comes again from philosophy and biology, the idea of building a self-model of the system. That's very important. And so once you have that self-model, you're able to reason about that self-model. And I want to distinguish between two specific kinds of policies and situations that you have. The first is what you might see in biology, which is the autonomic system, where you have reflexive responses. So this is an example where the actions are driven solely based on external feedback. So if you touch something hot, you'll jump back without even thinking about it. The other is the complementary system of reflection and introspection, where you're thinking about things and you're planning ahead in the future. You're evaluating different choices and making choices in the future. So you're combining both stuff in the past as well as in the future. And so I think what we want to think about these two systems, the fast and the slow, if you want to call it, or the reflexive, reflective, or the reactive and introspective, are very complementary and should be used when we try and design these adaptive systems. So what does that mean in terms of chips? So this little cartoon here shows you a chip where we have a bunch of these red dots that represent sensors. These are your physical and virtual sensors. They may be circuit-level sensors. They may be packet inspection engines. They may be registers that capture architectural events. They may be program counter type things, et cetera. And what we typically do is we have these adaptations where we have policies that allow us to monitor something and then go back and make a change based on some policy. So for example, if you notice that the temperature is high, you may have a policy that says, well, let's do some migration, let's throttle the frequency or do something like that. And this is what I would call as a traditional reflexive or reactive model. Complementary to that is something which is self-aware, where you want to do some self-modeling. So you want to take that chip and build a model of the chip and execute that in parallel. And that model is going to go in and affect how you change your policies over time. So if you're moving from a high sort of a performance-oriented goal to maybe thermal design power, you can switch policies. You can change your policies over time. And so this is what I would call as your model that includes reflection and introspection. And these two systems operate in parallel at different time scales, perhaps, but they operate in parallel. So, you know, a lot of today's policies that we see are indeed inherently reflexive, and they're reactive, because they're control loops where you build a model, you sample what's happening, and then you act in the future. And so this is typically what we think of as an observe, decide, act loop. And so in this model here, you do some sensing, you do some actuation, and then you may do that at different time scales depending on the policies. 5 minutes, right? So this is as opposed to the reactive, the reflective approach, where you might actually do a what if, where you model some actuation, and then you see what the effect of that is, and then based on that actuation, you would actually do things to try and decide what to do in the future. So these two loops should perform in parallel. So, you know, I don't have much time. I want to talk about the fact that we have built a system that does that for runtime allocation. And we have this model called MARS, which is middleware for adaptive reflective systems. And it really has these different ideas of the cross-layer abstractions for sensing and actuation that you can see here in this system stack, where you sense and you actuate. And then you have the traditional control loop where you can do your simple loops. And then we also have the other loops, which is a reflective model, where at each level of abstraction you have a model representing that abstraction. And that allows you to think proactively to decide what to do in the future. So I have some examples. Don't have time for that, so let's skip that. And there's some, and if you're interested, we have open source software for that. So, you know, you have the slides, go take a look at it. The paper, a couple of papers appeared in Codes ISSs in some other areas, so you're welcome to take a look. The last part I want to talk about is the idea that, you know, this is all nice, that you can be self-aware and self-adaptive, but we want to have bounded behaviors. So there, the metaphor we want to look at is this notion of trying to achieve a goal, and I'll use the metaphor from bowling here, where you want to be able to achieve a goal where you want to strike that pin. That's your objective, right? And the problem is that if you have an ideal model, it works well. But the problem is that you may have a lot of variances in your model. Maybe the sizes of the balls are different. The person who's bowling may have a different amount of energy. Maybe the surface is variable, et cetera. So because of model imperfections, the strategy that you use for your goal may go off track. So what we want to be able to do is to have some idea where we can constrain the behaviors so that we're always reaching that eventual goal. And so this metaphor of using bumpers on the side, for example. That's if you're trying to achieve one goal. But as we discussed, what we typically have is the idea that you may have multiple goals you're trying to achieve that vary over time. So again, having this idea of having some notion of supervisory control will allow you to try and achieve these goals in a bounded manner. And to do that, what we have done is in ASPLOS 18 earlier this year, we had a paper which had this unfortunate title called Spectre when we submitted it, and when it got accepted, you know, the bug came out. But anyway, so this is a different Spectre without an E. It's the artist without an E. So, and here what we have is this notion of having these different low-level controllers that try to control different components in your unit, together with a supervisory engine on top that tries to bound the behavior of these controllers in a coordinated manner. So that's kind of the idea that we have, and we've shown how you can use this in a heterogeneous multiprocessor like an ODROID platform with the big.LITTLE platform. So that's what we've shown. If you look at the paper, you'll have more details on that, but it sort of gives you an idea of how you can do this. And we have some interesting experiments which show how you can do this in the context of running this QS application here with some non-QS applications and looking at how you can actually manage both. This is frequency, this is performance really, and this is power. And so if you have some particular metric that you're trying to reach here, we can guarantee in different conditions with different mixes of applications that we can actually achieve that. So it looks like a very promising approach that we can look at. So let me wrap up in the minute that I have. So I talked really fast, but there were a couple of key messages that I'd like you to take away from this talk here today. And the first is this notion of this idea of cross-layer physical, virtual sensing and actuation. The idea of being able to model an abstraction stack and gather interesting information so that you can actually combine that in interesting ways. And the way you'd combine it is using this notion of going from today's chips, which are primarily reflexive and reactive, to having these be both reflective, reactive, and introspective, where you can build a self-model and try and predict what might happen in the future and do that in interesting ways. So that's sort of the second key takeaway. And the third is, this is great, but what if it doesn't behave the way you want to? Then what you really want is this notion of having also supervision, maybe adult supervision, so that these kids don't go astray, so to speak. So the idea of how do you actually control and coordinate that in some manner. So that's it. If you're interested, there's more information on self-awareness. We had a special issue in Design and Test that talks about computational self-awareness for chips. And there's also a workshop series called Selfish, which is self-aware cyber physical systems. So I invite you to go visit that, and maybe we're trying to build a community of people who look at this and understand what this means for systems. So that's it. Let me wrap up by thanking you and taking questions.
Any questions in the room? Hi, thanks for the talk. Andrew Anderson from Trinity College Dublin. I'm wondering if you think it's feasible for this kind of prediction to eventually make its way into hardware, much in the same way as, for example, branch predictors. So is it a feasible kind of thing that you could actually run in silicon as opposed to being in software in a runtime?
Yeah, funny you should ask. I have actually a slide on that. Let me just find this. So it's all about the time scales at which you're doing this and the resources you need. And one of the recent projects we have at TU Munich is exactly doing that in hardware. So let me just put this slide up for a minute. So the main question that really you're asking is, can we afford to do this kind of reflection in hardware, software at different time scales? And so this slide here says, you have time where you have very fine-grained time here, you have coarse-grained time here. And depending on the kinds of policies that you're developing, you might be able to embed that in scheduling, for example, at a very fine level. In fact, our colleagues at TUM are using very simple lookup tables and using that to try and dynamically change that, versus something maybe at the policy level of dynamic voltage frequency scaling, versus something where if you're doing something for wear leveling, the time intervals are very, very long. So maybe you have different policies. So absolutely, you could embed them across the stack. And I argue that you should think about how to place these very carefully at different levels of abstraction. Yes?
Hi, this is Florian de Teresa from Quantum Light and the Maxwell Center. And this is just, I guess, philosophical reflection on the meaning of awareness, in the sense that I'm getting that you are basically assuming that we have an algorithmic type of computational awareness. So this would go to the heart of this Howard Gardner's, whether awareness is computational or it isn't, and this Roger Penrose, the shadows of the mind. And could you comment on that?
Yeah, I think we want to be very careful when we use the word awareness, which is why I actually always qualify that by saying computational awareness. Because we don't want to get into philosophical discussions of, what is the meaning of the soul and awareness and all this other stuff, right? So I think this is really from an engineering perspective, where we can build self-models of the system and use that to do predictive analysis and maybe do machine learning, applied machine, all that other stuff. So I really want to qualify that by saying it's computational self-awareness, which is maybe a very, very restricted version of the broader meaning of self-awareness.
So we're not going to build data?
Say again?
Data from Star Trek is not in
No, I don't think so.
Any other question? So I have one myself, maybe. Trying to steer it towards the machine learning. So you mentioned that it's a possibility to use machine learning in, I guess, in the models that you have embedded in the system. Any example of?
Yeah, I mean, you know, I think Ben had a very good kind of line there, where it's not just about, you know, traditional classification machine learning. So, you know, for example, we're looking at very simple reinforcement learning rules with lookup tables in hardware. Someone asked about that. So our colleagues at TOM are doing that. So depending on the time scale and the amount of data that you have, you'd have to use very different strategies. And so I think this is a great goldmine for people who want to look at exploring things across different time scales and also dealing with different levels of data. For example, his talk had gazillion amounts of data, but here you're sensing information, but you may not have the capacity to get that much because you may have limited resources. So even with that, you can still do interesting stuff, but it requires a different view of what you mean by machine learning, right?
Thank you. Let's thank the speaker again.